Hello! And just when you might have felt like you'd finished learning all about matrices, it turns out there's still a lot more to learn about them. Because ultimately, the higher and higher you go studying mathematics, the more matrices tend to crop up due to their importance in helping deal with both multi-dimensional problems or multivariable problems. Today, we are introducing something known as eigenvalues and eigenvectors, specifically focusing on just how to do this stuff with 2x2 matrices today, but yes, you can do it for 3x3 matrices too. And post-editing Greg here, this video was originally going to be twice as long as the one you're watching right now, because I wanted to both show how to find eigenvalues, etc, but also to make sure that I explained what these things actually mean and why they're so important. However, because I realised this video might end up being way too long, I split up into two videos, and this particular video is just looking at the what, but because I still think the why is so useful and more importantly interesting to know, we will have a video looking at that as well. The link to that video will be in the description of this video when I've actually got around to uploading it. And let's get started straight away by showing you how to find the eigenvalues of a matrix. If you have a matrix M, if you want to find the eigenvalues, you've got to start by taking away lambda lots of the identity matrix, where lambda is the unknown, currently algebra letter representing the eigenvalues you're trying to find. In order to find what those eigenvalues are going to be, you've got to take the determinant of this matrix and set it equal to 0 and solve to find those eigenvalues. Therefore, if we're just applying this idea to 2x2 matrices, if we start with the matrix A, B, C, D, if we're taking away lambda lots of the identity matrix, then ultimately because of where the 1s are placed in the identity matrix, we end up effectively only taking away lambda from the elements in the main diagonal of the original matrix. Therefore, we're calculating the determinant of A minus lambda, B, C, D minus lambda, and then we're setting that equal to 0, and as I said, solving to find the eigenvalues. It really is as simple as that. So let's get started straight away. We've got an example, we've got a matrix, and we've got to find the eigenvalues. Some people, when they're setting this stuff out, like to start by literally writing it as the original matrix minus lambda lots of the identity matrix to write it out fully. But after doing this a few times, admittedly, normally what I do is just skip straight ahead to effectively just writing the original matrix, but with minus lambda included as part of the main diagonal elements, and then all the other elements of the matrix staying the same. And then, as we mentioned, to find the eigenvalues, all you've got to do is do the determinant of that matrix and set it equal to 0. So therefore, that is what we're doing here. So to work out the determinant of a 2x2 matrix, of course, we're going to do that main diagonal multiplied together, take away the elements in the other diagonal multiplied together, which, if we multiply out the brackets, will get us lambda squared minus 7 lambda plus 12 minus 2, which simplifies the very nice quadratic lambda squared minus 7 lambda plus 10 equals 0. And the reason that is so nice is because this is one that just factorizes very nicely. We're going to get lambda minus 5, lambda minus 2, which therefore means our eigenvalues for this matrix are lambda equals 5 and lambda equals 2. And genuinely, we're done at that stage. We've found all the eigenvalues. What on earth are these things? We will explain in the future, but for the moment this is just how you find them, and it really is that easy. But how do we find eigenvectors? Well, the first thing to bear in mind is that eigenvectors are paired with a particular eigenvalue. So you need to find the eigenvector that goes with each of the eigenvalues you found for the particular matrix. And in the case of 2x2 matrices, eigenvectors will be 2D vectors. In other words, a 2x1 matrix, such as this vector you can see on the screen right now. The vector in that case, therefore, if it's going to be an eigenvector for your matrix, will be a solution to the matrix equation m times by x equals lambda lots of x, where m is the matrix we're looking at, and lambda is the eigenvalues of the matrix we were dealing with. So, therefore, let's apply that here. Obviously, therefore, the first step to finding eigenvectors of a matrix is to find the eigenvalues, but luckily, we've already done that for this particular matrix. We already found that the values were lambda equals 5, lambda equals 2, but therefore all the working we did before is all feeding into part of this overall method. So how do we then find the eigenvectors? Well, we've just got to set up that matrix equation we had before. We've got 3, 2, 1, 4 times by the 2 by 1 matrix xy, or the 2D vector you could view it as, and that's going to be equal to a eigenvalue. We've got to do this process for both of them. Let's start off with that eigenvalue of 5 times by that same 2D vector. So we've now just got to solve this matrix equation. So I'm going to multiply out the matrices on both sides, so therefore on the left we'll end up with 3x plus 2y equals 5x. Interestingly, that simplifies to, of course, being 2y is equal to 2x, meaning you end up with y equals x. Now the thing is, this bit of algebra we've just found is telling us the relationship between the x and y values in our eigenvector. Whatever the y value is, it's got to be the same in this case as the x value in that vector. The thing is, there's loads of different values that satisfy that relationship, but the good news is, because we're talking about vectors, we can choose any value, any pair of values I should say, that do satisfy it, because if we do pick a different set of values, all that would result in is a parallel vector to the one we had before, which is ultimately just fine. So therefore, an eigenvector for this particular matrix we're looking at would be 1, 1. I could have technically alternatively picked 2, 2, 3, 3, 4, 4, etc, etc, but 1, 1 was the most logical, simple eigenvector I could have written, so that's why it's the one I chose. Now, interestingly, some of you are probably looking at this going, wait a minute, I didn't fully multiply out those matrices properly. I only did the top row times by the 2 by 1 matrix. Well, here's the thing. You should do it with the other rows as well, just to check. But interestingly, you should, a lot of the time, get the same answer. So for instance, if I now do the 1, 4 times by the xy on the left-hand side, that would lead to x plus 4y, then equals 5y. And if you simplify that, that will lead to us getting x equals y, which is of course the same relationship that we had before. Now, as a result of these things ending up being the same, that's why some people don't actually bother to fully multiply out those matrices on the left-hand side, because even just doing the top row in that first matrix followed through in the equation is enough to tell you all the information you need. However, sometimes it is a good idea to do both just to check, partly just for your own confidence that you've got it right, but also because sometimes one of the equations you'll get from doing this process will end up being slightly more vague than the other equation you'll get. So by considering both, we'll make sure you're abiding by all the constraints that are needed to be met to find your particular eigenvector. But anyway, that was just the eigenvector for the eigenvalue of 5. We also need to find the eigenvector for the eigenvalue of 2. So repeating that process with the eigenvalue of 2. So set the matrix times by xy equal to that eigenvalue times by xy. Multiplying out those matrices, we get 3x plus 2y must equal 2x by doing the top row, and then doing the bottom row, we'll get x plus 4y is equal to 2y. As I mentioned, technically a lot of the time you wouldn't have to do both of these things, but again, if you just want to check and be doubly sure, then by all means do it. It's good practice to do. But anyway, then simplifying both of these relationships, the top one will end up simplifying to 2y equals minus x, and that bottom relationship will end up simplifying to x is equal to minus 2y, which is technically the same as minus x equals 2y. So there you go. As a result, we can pick any x and y value that satisfies this relationship, but therefore I'm going to go with, let's say x is equal to 2 and y is therefore equal to minus 1, because that would work in that particular equation. So there you go, those are our two eigenvectors, 1, 1 and 2, minus 1. There are alternative answers, but they'll just be vectors that are parallel to the two vectors I have written here. However, we do have to be careful with this process. Most of the time, the matrices you're looking at will have two eigenvalues, two distinct eigenvalues, whether that's two real eigenvalues or two complex eigenvalues, because you can get that happening as well. But either way, it's still just the same process, just whether it's all with real numbers or all with complex numbers. But the situation you have to watch out for that can sometimes be a bit tricky is the situation where you've got repeated eigenvalues. And I'm now going to show you a couple of examples of matrices with repeated eigenvalues, just so you can see some of the nuances you have to watch out for when dealing with them. So the first example we're going to have is this one here. So this time you'll get to see the full process because, as I mentioned before, part of the process of finding eigenvectors is starting by finding eigenvalues. So let's start by doing that. So therefore we know that the determinant of 7 minus lambda minus 4, 1, 3 minus lambda has got to equal 0 if lambda is the eigenvalues. So therefore we end up with 7 minus lambda times by 3 minus lambda minus 4 times by 1. And that's set equal to 0. That will get us a lambda squared minus 10 lambda plus 21 plus 4. Which means we get the very nice quadratic that looks like this, which means that we end up with repeated eigenvalues, surprise, surprise, or not, because I already signposted that we're looking at an example that did that, but our repeated eigenvalue this time is lambda equals 5. But then, therefore, to find the eigenvectors, we're going to take our matrix, multiply it by the mystery eigenvector xy, and set it equal to the eigenvalue lots of that same vector. And then we've got to solve. So therefore we will get 7x minus 4y equals 5x, and then the other relationship would be x plus 3y equals 5y. Now if we simplify both of those relationships, the top relationship becomes 2x is equal to 4y, if we rearrange that a bunch, and therefore that will simplify to x is equal to 2y. Okay, then looking at the other one just to check, we will end up with x equals 2y a lot more quickly. And therefore our eigenvector could be if y is equal to 1, then x must be double that, so therefore it's 2. And interestingly, in this particular case, we are done. That is the only eigenvector. We only had one eigenvalue, and therefore that is why we only had one eigenvector, and therefore we are done for this particular question. But the confusing thing is that not all matrices that have repeated eigenvalues only have one eigenvector. There are some that will have technically infinite eigenvectors. Let's take a look at what I mean there. So let's look at another example. This time we've got this matrix. Again, we could find the eigenvectors very quickly by just taking away lambda from the main diagonal, keeping the other elements the same, finding the determinant of it, and setting it equal to 0. So in this case, interestingly, once again, we are going to end up with repeated eigenvalues. And again, interestingly, it's going to be just lambda equals 5. But then when we start trying to find what the eigenvectors are going to be, we write our matrix out, we write the xy, set it equal to 5xy, and then start to solve. Interestingly, we get 5x is equal to 5x, and we get 5y equals 5y. And the problem is with both of these relationships, they both just boil down to 0 equals 0, which is reassuring because it's true, but it doesn't actually tell us anything useful about what x and y must be. And that's because actually there's technically no restrictions on x or y for this particular scenario where we're trying to find the eigenvectors for this particular matrix. Therefore, you can actually pick anything. However, because of some of the things you're going to be doing later with eigenvalues and eigenvectors, in an ideal world, we'd like to have two eigenvectors written down, because most of the processes we do with the eigenvectors of 2 by 2 matrices involve needing two of them. But which two vectors should we pick? Well, you should pick two vectors that are what is known as being linearly independent of each other. Now, linear independence for vectors just means that if you have a set of what you're calling linear independent vectors, then all the vectors in that set are vectors that cannot be written as a combination of the other vectors in that set. In the case of real two-dimensional space, that means we only need two vectors, and we just have to make sure that one is not a multiple of the other. In other words, we just got to pick two vectors that are not parallel to each other. So you can, as I said, therefore pick any two vectors that are not parallel to each other, because this particular matrix has infinite eigenvectors technically. But the general convention for this situation is to pick the two nicest vectors in 2D that we've ever come across, which is basically the I vector and the j vector. In other words, 1, 0 and 0, 1. As I said, these aren't the only answer you'd have to use, but they're just the nicest and best to use ones based on what we often like to do afterwards later on with eigenvectors. And there you go, that's it, that is how you find eigenvalues. And therefore, that is where I'm going to cut it for this video today. We aren't done though. I want to explain to you why these things are cool, why they're useful, because at the moment, if you just watch this video and nothing else, this process is going to seem so random and just sort of out the blue, kind of almost pointless, but it really isn't. Trust me, there's so much cool stuff to do with this. So therefore, check out my next video when it's released on eigenvalues and eigenvectors, because we'll be explaining why we care about them. See you in that video. Goodbye.